When we think about fire ecology in forests, probably no system has had a strong influence on how we think about fires in the western United States as ponderosa pine forests of the Intermountain West and southwestern US. Because of a long history of fire suppression in these forests, there's been a real strong need to get in and work with the management of these systems in a way that brings back a fire ecology that has been common in these systems for close to 500 years or so prior to Euro-American settlement. So it's well recognized that in the southwestern US and the intermountain US, fire suppression in systems that previously were dominated by old growth ponderosa pine with a grass and light understory um, and lightly vegetated understory. Fire suppression in those systems has led to rapid growth of young trees, small trees that we call doghair thicket stands. So small pines that have come in and filled in the underspaces that used to be dominated by grasses. This has led to a dangerous situation in a lot of these forests where without fuels treatments, if we get fire into these systems, we have ladder fuels that rapidly can carry fire up into the canopy and take a surface fire and turn it into a crown fire. There are hundreds of papers on the fire history of these systems, and there are many more opinion pieces arguing for the importance of reintroducing fire and actually introducing non-commercial thinning operations in these forest systems in order to thin out the thick doghair thicket, uh, pine seedling understory and restore grass understory and frequent fire to these systems. Here's a graphic illustrating the same idea. And so if we think vertically in our forests in terms of where the tree crowns are and where the surface is, we can think, okay, the understory really serves in a fire scenario as a surface fuel. Then we have ladder fuels. So we're beyond just the fire behavior triangle of just fuels being one of the elements of that triangle. And we're starting to think, okay, those fuels can be ladder fuels, they could be surface fuels, they could be large, they could be small. And if we have a lot of surface fuel and we have ladder fuel with small trees, we have a scenario where a surface fire can rapidly move into a hard to control crown fire that can spread quickly and end up with a large footprint on the landscape. Very large acreages can burn in that scenario. So many scientists have argued that we have a scenario where we're in the current condition, and what we really need to do is change the structure. And so we're going to take the structure of these forests that have these high uh, density understories with a lot of doghair thicket trees, dry, small diameter trees, and we need to move from those current conditions into a little bit more simplified forest structure in the sense of removing those trees so that we can change the process from these kind of um, high probability crown fire um, systems into into low probability crown fire systems where we can have a regular reoccurring fire where we have low intensity, high frequency fires with a low probability of crown fire and a low time for recovery following a fire. So the number of years between surface fires becomes low, the probability of a crown fire becomes low, and the time to recovery in the system becomes low. So we have a high resilience to fire if the structure is right. The structure is low tree density, low vertical continuity, and low horizontal continuity. An idealized forest might look something like this once it's restored. And there are, again, hundreds of examples of this within the Southwest and Eastern Washington, Eastern Oregon forests, where previously forests that were dominated by doghair thickets can be restored such that the old growth trees are able to survive. We have healthy grass and wildflower communities underneath these forests. These are park-like settings. In some places in the Southwest, the lore was that you could ride a horse in any direction through these forests at full speed without hitting anything. That's how open the forests are. So this is a very compelling story, and it makes clear sense for these forests that if you get in and you work with these forests to get them back to a structure that they looked like before European settlement, that we might have a healthy fire regime where we can live better with fire, reintroduce fire, work with fire better, have it present in our landscape. And in fact, a lot of these landscapes that are dominated by ponderosa pine, we go further and say that instead of thinking of forests in terms of, um, you know, the initial stages of succession or pioneer succession all the way up to climax, instead of a climax forest type, we might call this a pyroclimax or a fire climax. That is, this is the final stage of succession for these forests in the presence of fire as a natural phenomenon. Okay. But this is one type of forest. And so there are forests that certainly match the paradigm I just outlined there. And then we have forests like we see on the Olympic Peninsula or in Western Washington. They look a little different than those ponderosa pine forests, and we shouldn't fool ourselves about that. So here's a late succession mixed conifer forest in Oswald West State Park on the coast in Oregon. Looks a lot like forests along the Olympic Peninsula. Pause and take a look at this photo. Um, where are the ladder fuels here? Are those natural or unnatural? Are those a result of fire suppression? So when we look at a photo like this compared to what we look at here, here we could be looking at a pre-settlement forest, a forest that has an open structure before Europeans arrive. But here we could also be looking at a pre-settlement forest. But this forest, an old growth forest in Western Washington and Western Oregon, would have a high ladder fuel, high vertical continuity structure that is consistent with the climax and natural development of these forests in the absence of human intervention. In other words, this is what an old growth forest in these systems looks like. This is what a primeval forest in these systems look like. And if we think about this current conditions, structure, and process scenario, the current conditions for these old growth forests looks a lot like what their natural succession conditions would look like. How about here? Let's not leave out our deciduous forests. In this system, do we have ladder fuels? Absolutely. Some of those ladder fuels are epiphytes. These are all from the Hoh rainforest on the Olympic Peninsula. And could fire move up these moss mats into the tree canopies? Absolutely. You have flammable material in a dry year all along the trees. We have a lot of ladder fuels. We would be foolish to think we should go through and remove all those ladder fuels from a natural forest like this. In fact, in some places in the Northwest, we might try to do that and it might not work. Imagine taking a forest like this and thinning it out to look like an open-grown ponderosa pine forest. So the east side, dry Intermountain West fire paradigm looks something like this. Natural, healthy forest is what we're seeing up top, where we have open space trees and regularly occurring fires that come through and burn surface fuels. It's a low intensity burn, and the trees are left standing, and the system can maintain that way in perpetuity, hypothetically, as a pyroclimax. With fire suppression, we get the buildup of small diameter trees and ladder fuels in the understory that carries fire into the crown and can destroy huge swaths of forest. A really important concept for many forests. And I've certainly worked in forests that look exactly like the ones up top, where I've seen fires with evergreen students. We've been in the presence of fires that are burning through lightly in the understory, so lightly that right after the fire comes through, you can go through and sample for the effects of the fire on the system. You wouldn't want to be present in a crown fire condition like at the bottom of this photo. It turns out that the natural condition of an old growth forest in Western Washington might actually look a lot like that other scenario. So an old growth forest in our Western Washington systems are really set up that in a dry year, if the weather conditions are right, they can look like that Bambi image of disastrous wildfire in the presence of fire. We're going to come back to that in a second. But it's because it's a lot more complex than that. This map is a map that was made to show different fire regime groups. And there have been a couple attempts to do this in the Pacific Northwest, where we shouldn't think of the Pacific Northwest as just having one fire regime, but in fact, there are multiple fire regime types that are all occurring at the same time across our landscapes. We have a tendency to think fire is one type, forests are one type, when in fact, they're much more complex than that and much more differentiated than that. In 2020, we had tremendous fires on the West Cascades in Oregon. On this map, these areas are all in the yellow. We would call this fire regime group 3, according to this map and the authors of this study. And in fire regime 3, we'd have a fire return interval that could be anywhere from 35 to 200 years. It's a pretty wide range. And within that fire regime, we might have kind of some mixed severity for us. So not all trees die. We can have widespread large fires, but we should have patchy mortality patterns. So we have patches of forest that survive, patches that are severely burned, patches of low intensity fire and surface fire, and patches of a lot of patches of ground fire, and then patches of high mortality ground fire, all within the same mosaic. As we move into wetter forests of Washington and especially coastal Oregon, then we turn into these systems where we have over 200 years between large wildfire events, like what occurred with the Tillamook burn. And these tend to be high intensity crown fire scenarios when fire does occur. And that's natural. That's without human intervention. So what becomes really difficult is put humans in the mix, move them into that scenario. 200 years later, wildfires erupt, and what do we do about it? So this has led multiple authors to think of fires in terms of climate-driven versus fuel-driven systems. And so there are some systems where we're going to say this is just a climate-driven fire scenario. And so this would match the conditions of, for example, Western Washington, Oregon Coast Range forests, where we have forests that naturally grow to an incredible density, to a situation where there's a lot of ladder fuel, a lot of vertical continuity from the understory all the way into the overstory. In fact, that's critical for good old growth habitat for flying squirrels, for example, or spotted owls. You need that forest structure. But when fire hits it in the wrong climate conditions, then all of a sudden you can have disastrous scenarios for crown fires. On the other hand, we have fuel-driven systems, systems that are really just driven by the abundance of understory fuel that can be unnatural. And so in the case of a fuel-driven system, if you let those understory fuels build up, then you end up with these massive crown fires. But in the absence of that, you could maintain the system with regular low intensity fires, like the Ponderosa Pine system. So I think this distinction is really important to bring up, especially because in the climate-driven system, there might be very little you can do to prevent really large wildfires other than having plans to protect humans from being impacted by those fires, especially in the presence of climate change. There are many ways to look at the history of wildfire. Here's some graphing of the history of wildfire in recent time, demonstrating increases in fires through time in the Western United States. This is lumping all sorts of different forests all together and then analyzing them by color. But as we can see, even the Washington and Oregon groups are, a lot of our Cascade forests are all lumped into one category here. What you can see is that across most of these fire regimes, except for Mediterranean California, at the end of this study here, through 2011, we had increases in fire, in number of large fires in all of these systems. And so undoubtedly, fires are changing through time. How do we know about fires and their extent and their changes through time going back before we could map them? Well, it turns out that there are really nice, simple ways to go through and understand the history of fire. And probably one of the most important tools in understanding history of fire that predates the current era is by using fire scars. So fire scars allow us to travel back in time. When a tree has an open wound on its face, or what we might call a cat face, um, or is commonly called a cat face in um, the common parlance, um, a fire can burn through and then burn the insides of that tree. And as it does, it can scar along the healing margins of the cat face or open wound. So if we have a fire that's burning, this is from a 2020 photo in the redwoods where fire is burning inside of a tree. It's a dramatic example. Most of the time it's less dramatic and might look something more like this. We have a tree scar that's healing. But every time a fire comes through this system, it's going to burn in along the margins where there are sugars and saps and bark trying to heal over that scarred material. And every time it does that, we're going to get a little fire scar that goes into the tree ring record. So taking a cross section of this cat face, we can actually sand down that cross section and look at it closely. And by dating the tree rings and then finding the tree scars, we can actually look at the frequency of fire in that system, high severity or low severity. This would be a tree that um, has lived through multiple fires. If we do this for enough trees, and there are ways to even do this for dead trees and match them up with live trees, then we can come up with maps where we found these fire scars on the landscapes. And so once we've found enough of these fire scars and we've been able to date them, we can use that information to spatially interpolate the locations of fires. For example, here's a map from the Olympic Mountains in northwestern Washington. And this map is dividing up fires into human-caused versus lightning-caused fires based on other evidence from the area. You can see that even the Olympic Mountains of northwestern Washington have a dense fire history that is more concentrated in this case on the more arid, more rain shadow end of the Olympic Peninsula, which is towards Port Angeles and Port Townsend on the northeast corner of the Olympic Mountains. But regardless, throughout, we have a large density of fires that in this case are burning, very small acreages, less than an acre, all the way up to, in this case, about 1,300 acres. So in most fire scenarios, we'd see these as small fires. We can take data like these where we have all of these fire scar histories and their point data, but we can interpolate them into a raster using what we call spatial interpolation techniques, where we use models to determine what we expect the interspaces between these dots to look like and come up with maps of expected fire history across the landscape. On the left here, we have an image from the Central Cascades in Oregon, and this is estimating the fire history between 1800 and 1900 in this forest. The black areas indicate about 70 to 100% mortality. Dark gray indicates about 30 to 70% mortality, and light gray is about 30% or less than 30% mortality. On the right, we have a graph that is again coming from Perry et al. That is showing the number of acres in mortality classes, and then the mortality classes are arranged from left to right, starting with over 75% mortality and ending with less than 10% mortality. Let's talk about the panel on the left first. This camouflage pattern on the landscape, we're looking at an aerial map, an interpolated map of fire mortality in these old growth forests that are essentially pre-settlement. And what you should notice from this is a mosaic of mortality patterns. So this would change your perspective from thinking about fire as this Bambi-style complete forest destruction event in Western Washington forests to thinking of fire as more of a influence on system diversity. It's influencing landscape heterogeneity. It's diversifying the system. There are patches of high intensity crown fire for sure. There are also patches of low intensity ground fire, and they're all intermixed. So a forest following this fire is going to develop probably more diverse than it started before the fire. So this is going to be a diversity enhancing event. Is it going to be severe? Absolutely. Is it going to look dramatic? Are you going to lose large old trees? Absolutely. And is it going to be a problem if people have built their favorite cabin in the woods in the middle of these forests? Absolutely. But the ecological consequences might be less severe than we might think at first. Interestingly, the graph on the right is showing data from Silver Fire in southwestern Oregon. And in this scenario, it's showing you the mortality categories, mortality classes, and the percent of acres. And what I want to point out first is that if you look at the top graph, you see the highest bar there. The tallest bar is in a less than 10% mortality class. Okay, that is almost 50% of the acreage of this severe crown fire event occurred. Almost 50% resulted in less than 10% mortality. Now let's read the title of that top panel. This is for mature and what they called over-mature conifer stands. In other words, old growth. So old growth forests had almost half of their area in this fire in low mortality classes. Sure, there were some high mortality classes, over 75% of the trees dying, but this was less than 20% of the landscape. Compare it with the panel below, where we have a small saw timber conifer stands, actually multiple. These are stands that are small diameter, they've been thinned, they've been actively managed, and now the mortality is actually spread so that we have 30% mortality. In the over 75% mortality class, we have over 30% of the landscape in that class. The 10 to 25% mortality has over 35, almost 40% of the landscape is there, and about 15% of the landscape is between 25 and 75%. We only have about 20% of the landscape that is less than 10% mortality. So what this data illustrates is that just managing the forest does not imply, especially in high severity fire situations or in forests that are prone to crown fires, just managing the forest does not mean that you've gotten yourself out of the woods with regard to high mortality fire events. And in fact, an old growth forest might actually be a little bit more resistant to large fire conditions than previously thought. Okay, just a few thoughts to leave us with as we depart from thinking about fire exactly this way in a single video. Our previous conceptions based on the history of fire scar research and understanding past fires can only get us so far. As climate changes, we know that climate is going to have a tremendous effect on fires. We know this from the history of fires in the Pacific Northwest. We know even the structure of our old growth forests in the Pacific Northwest is somewhat dependent on the deep fire history associated with a medieval warm period and the Little Ice Age. So we know that in the past, climate has had an integral effect on how our forests burn. Further, we know that we have a lot of climate-driven fire scenarios in the Northwest, where climate is the big determinant on whether a fire grows to massive acreage or stays smaller than an acre or smaller than, say, 1,300 acres, like the fire history in the Olympics that we talked about earlier. Layered on top of that, we have systems that we might previously think of as climate-driven systems, where we have old-growth forests, we have a lot of species that we wouldn't think of as being readily fire adapted, such as locations around Mount Adams. This photo is taken from a location um, that has burned 3 times, 3 years in a row since 2008. And so the Cold Springs fire burned this area in 2008. The Cascade Creek fire burned it in 2012. And then the Cougar Creek fire burned it again in 2015. This is in a system that supposedly would burn greater than, every 35 years, maybe up to every 200 years, we get a fire. But here it is burning again 3 times. Okay, does this remind us of the Tillamook burn? Yeah, a little bit. This can happen. We know that this is possible. But we're entering a phase in the Pacific Northwest where we have series of years that are dry enough with weather patterns that are dry enough that a climate-driven system can quickly be transitioning into a higher fire frequency condition. We're going to have to start thinking about systems transitioning from climate-driven to fuel-driven systems. We're going to have to start thinking about systems transitioning from a position where they used to be high intensity, low frequency fire systems to high frequency, low intensity fire systems. It has to change the way that we think about fires in some systems. We have to be ready to adapt. If the climate's changing and the time is changing, then we need to be thinking about changing too. Most importantly, though, I think the one lesson that we can take home from this brief lesson or this brief tour through fires and forest types across the Pacific Northwest is that one size just doesn't fit all. It doesn't work to say fire suppression everywhere. It does not work to say bring fire back and thin all forests for fire resilience everywhere. All forests are not the same. All fires are not the same. The climate is changing. So even if they were, the climate's going to change the forest you knew about into something different. And we have people in the mix. And as people are more present in these systems in the midst of forests, then we end up with a much more complex problem in some respects than we did when we were just thinking about the fires alone.